Hello folks. Okay, well, now that we've done kind of an intro to the course, I want to talk about functional programming in general, and then later on we'll get into Lisp more specifically. So I guess the first question is why? Why am I going to torment you with this? So I want to spend a little bit of time, we'll talk about the theory of functional programming in this session, and then in the next one I'll get into actually using Lisp, which isn't going to be very pure functional programming, but will take advantage of a lot of the features. All right, so I'm going to assume that you've got a pretty decent exposure to procedural languages, so things like C or C++. Well, I guess C++ is more of a hybrid, and you've got a decent background in OO programming. Right? Most OO programming languages give you a fair bit of exposure to the procedural side as well. So Java, again, C++. You've got a reasonable programming background in this, almost guaranteed by this point, but you probably haven't had a lot of exposure to functional programming. It's a very different way of thinking about problems and approaching developing solutions to a programming problem. So again, basically this expands the way that we're capable of thinking about problems. And it is actually going to give us different advantages and different disadvantages to a sort of procedural or an OO approach. Common Lisp is one of the widely used functional programming languages, although it's very much a hybrid of functional and procedural. And as we go through this, some of the things you'll see are the influence that Lisp has had on the development of other programming languages. Lisp is a very old beastie. It was one of the originals back in the 50s. And you can see features from Lisp that have crept into other languages over time, particularly with the OO side of things we'll see as we get deeper into the course. One of the things about the Lisp that we're going to be working with is that it's also a homoiconic language, which means that it can treat its own code as data. So Lisp can essentially read its own source code and treat the different pieces of source code as just regular Lisp data structures. So this makes it really interesting in terms of developing programs that can read their own code or read the code of other Lisp programs and modify them, generate other code. Introduces lots of really interesting possibilities. So in terms of the pure functional programming side of things, the basic idea is that everything is a function. You have nothing that is not a function. There's no variables, right? All you've got are function calls. There's no side effects when you're working with things. There's no explicit memory allocation and use. Everything is just done by function calls. If you've got something complex to do, then it's a function call whose parameters are function calls, whose parameters are function calls, and whose parameters maybe are actually your original data values, literal values. So it's really an interesting approach to try and work with. Your functions have no side effects. Again, there's no variables, so there's no global variables. You've got no access to shared memory. Functions are purely used pass by value. There's no reference parameters. Right? So a function can't have a side effect. And again, this leads to a very different style of programming. So if you've got some sequence of actions that you want to take place and a bunch of intermediate values, right, in terms of the way we usually think of a solution to a problem, you go, okay, well, I'm going to prompt the user, I'm going to read a value, I'm going to store it in a variable, I'm going to prompt them for another value, store it in a variable, then I'm going to do something with those variable values, then I'm going to print them out. Right? Usually we think of things in this very sequential style because that's the way we've been taught to program. So again, suppose we want to read a number from the user, compute the square root of it, add 10, and then print it out. Right? Usually you'd think, okay, well, I'll prompt the user, I'll read a value, store it in a variable, compute the square root, maybe store that in a variable, or maybe add 10 to that and store that in a variable and then print it out. So the way we would approach it in a pure functional sense is to say, well, ultimately what I'm interested in doing is printing the result. What do I want to print? I want to print the result of adding 10 and the square root of whatever the user entered. So the square root is supposed to be of whatever the user entered. So your composition is essentially, I want to read a value the user supplies, compute the square root of that, add 10 to the result of that square root, and then print the result of that. So this would be the style you'd look at in terms of function composition to carry out the actions that you want. Now, in most procedural languages, you could still do something like this, but we don't generally think of it because the language provides us with other means of doing things, and we have kind of evolved as developers to think, okay, well, I'll think of it in this sequential sense. So again, when this runs, it evaluates from the inside out, right? Evaluate the parameter, and then pass that to another function. Evaluate the parameters, pass that to another function. And so this is the kind of functional composition way of thinking about things. There are a couple of advantages. Sometimes we can express things much more simply in this kind of an approach. If you think of the cases where you've seen a recursive algorithm for doing something that's much simpler than the typical procedural approach. So you'll often see the same sort of idea where if I'm thinking just in terms of function calls and function composition, I can sometimes come up with a very simple expression for a solution to my problem. Not always. You're going to see times where it's the other way around, where there are some problems that it's much easier to express in a procedural fashion, or where the solution is easier to express in a procedural fashion. But there's definitely cases where the functional approach has a nice, elegant solution, if you like. One of the things that the pure functional approach gives us is extreme simplicity in testing complex programs. Functions can't have side effects, right? There's no shared memory we're accessing. There's no variables that are being set up and manipulated. It doesn't matter what order, if you like, functions are called in because we're doing this composition. So what that means is that if you test each of your functions individually, and if you've got 10 functions and you test each of the 10 of them by themselves, and each of them by themselves works correctly, then you're guaranteed that any composition of them is also going to work correctly. You don't have to worry about having one function called first to set up some global variable someplace, or to set up a value and then pass that on to somewhere else where it's going to modify the values that are passed by. So in a procedural sense, you often have this, in addition to making sure that the individual functions work, you have to worry that the side effects that they have also been tested in all the orders they can take place in. So this can make testing much simpler in a pure functional language. It also has an advantage of making it easier to automatically parallelize programs. So if you've got a whole bunch of processors and you want to be able to utilize all of them, but you don't want to have some great complicated algorithm to figure out the best way to distribute work across these different processors, in a pure functional approach, since these function calls are simply passed by value, no function can have an effect on what's happening in another function. Again, we don't have to worry about sequencing, we don't have to worry about state. If I have a function call that looks like f of, and I'm passing it 3 parameters that are also function calls, g of 7, h of 12, I of 60. I don't care what order g of 7 and h of 12 and I of 60 run in. I don't care if they run in parallel. I don't care if g and I get calculated first and then h gets calculated afterwards. If I've got free processors, I can just simply throw any function call at any available processor. It makes parallelizing things much simpler. If we don't have that, right, in a typical procedural approach, I have to worry about, well, is it possible that, G or H have got side effects that are going to impact one another, or that they're both accessing, some shared variable that they might manipulate, or some shared memory that they might manipulate? Is sequencing important? Right? So it does make for easier automatic parallelization of programs. Another advantage that comes with pure functional programming is proofs of correctness. This is kind of like the testing issue. If we've got a pure functional language and we're writing programs in it with a whole slew of different functions, if we can come up with, if you like, a mathematical or a logical proof for each individual function showing that it operates correctly, then we know that all possible compositions are also acting correctly, because they can't have side effects. Again, there's no state, there's no sequencing. We know that if they work individually, then they work collectively as well. So this does actually drastically simplify producing proofs of correctness for programs written in a pure functional form, compared to a procedural or OO type of approach. Of course, there's drawbacks as well. It's not perfect. The idea of having everything based on function calls means a lot of what we would think of in iterative terms in other languages are carried out by recursion, right? Recursive function calls in a pure functional programming language. And recursion is often regarded as not terribly efficient. And if we think of a typical implementation, every recursive call uses up more space on the runtime stack. You've got time to set up the call. You've got time to allocate the space on the stack, to copy parameter values into the space on the stack. So you've got the extra space that you're using and the extra time that you're using for all of these recursive calls, which can get to be quite a problem if you've got deep levels of recursion. So again, you've got memory issues, you've got space issues, you've got time issues, and that's seen as one of the great disadvantages of languages that are heavily driven by recursion. Now, there are solutions. If you can come up with an iterative solution for something, then you can also come up with what's called a tail recursive solution that uses time and space that are proportional to the iterative solution. So if you can do it efficiently in an iterative fashion, you can do it efficiently using recursion, but setting up tail recursive solutions can be quite a bit more complex and quite a bit less elegant, if you like, than the traditional simple recursive solutions for a similar problem. So we will look at tail recursion a little later in the course, but again, it is something that we have to be aware of, something that we can take advantage of. And actually, we'll take a look at how knowledge of tail recursive techniques can help us in other languages as well. And if I'm playing in C and I know that my compiler can recognize tail recursion and optimize it away, then I can effectively use tail recursion in C to get efficient recursion. All right, other problems. Duplication of computation. So let's suppose that we're using this pure functional approach, and I've got some function, so I've got my function foo, and somewhere inside it needs to use the value of some expensive computation multiple times. So let's say foo is going to work on g of f of x and on h of f of x. So since all of this is passed by value, and since I don't have shared memory or anything like that, then I'm really in a position where I'm having to calculate f of x twice, which again is slow and expensive if this is a nasty computation. So in terms of coming up with a reasonable solution that's still functionally pure, one of the things that you can do is to add essentially an extra layer, where what we'll do is instead of having foo call, or instead of having it call the function twice, what we'll do is have some top level function that passes f of x as a single variable to an intermediate function, which then goes off and uses that to call, say, g of a and h of a. So you add this extra layer of a function call and use its parameter twice. So you can come up with reasonable solutions to work around this, but it is something that you have to think about if you're trying to stay in a pure functional form. All right. Other problems. If we do want something done sequentially, it can be difficult to force things to happen in the exact order that you want. So for instance, suppose I want to prompt the user first and then read in a value. So if I've got some function f and I want it to give a prompt to the user and I want it to read in a value, that can be tricky to do. If I think of things like, okay, well, what I'll do is pass f the prompt and I'll pass it the read instruction or something like that. How do I know which one of these things is going to get evaluated first? Right? We were talking about the issue of parallelization earlier. Many compilers and interpreters that drive pure functional languages will try and come up with their own best order to run or to evaluate the parameters in if we call a function and pass it multiple parameters. So when we're the developer writing the function call, we don't actually know which of those things is going to get evaluated first. Right? So sequencing can be quite a tricky problem. You might wind up doing something like rewriting your function so that the first step, say the prompt, is done by a function call that passes the result of the prompt, if you like, to another function that does the read, that passes the result of the read to the function that's going to use the read value. So you do have to think about how to structure your calls to get the sequence that you want. All right, so there are advantages and disadvantages to pure functional languages. So just like with most other language paradigms, a practical language will typically appear in a hybrid form. So rather than being a pure functional language, it'll be a language that provides you with functional capabilities, but it might also give you OO capabilities. It might also give you procedural capabilities. Right? We looked at, in terms of OO languages, a typical OO language is actually a hybrid of procedural and object-oriented. Right? It gives you pieces of both, but it's not pure in either form. Same idea with most functional languages. Most of them are not pure functional languages. Most of them give you some kind of hybrid just because it's convenient for the developer to be able to use different styles at different points within the program. So you lose some of the advantages, but you also get rid of some of the disadvantages of the pure form. So we're going to be working with Common Lisp, which is very, very much a hybrid of sort of a procedural and functional language. All right, next time around, we'll get into playing with Lisp itself.